Welcome everyone. Welcome back to this discussion on equilibrium and dissociation. So we have been looking at different ways in which we can come up with the equilibrium composition for different reactions of interest, be it combustion or be it steam methane reforming, like one of the problems that you will solve in your homework. Now, what we want to do here is to show you the general uh, overview of how to solve such kind of problems and compare our results with the results of an equilibrium calculator available on the link below. Now, this is one of the many equilibrium calculators you can find, and the idea is just to tell you that, look, if you're looking at a certain reaction and you know what conditions you're looking for, then you should be able to get something similar, either by doing a calculation if needed, or from the calculator itself. All right, so let's get going with this. So here we are looking for a rich methane air mixture. Okay, and its equivalence ratio is given as 1.5. And for this, we need to calculate the mole fractions of CO, CO2, H2O, and H2 at 1500 Kelvin and 1 atmospheric pressure. Okay, so there will also be, of course, nitrogen on the product side, but it's not taking part in the combustion. And for this purpose, we have told that we can make use of water gas shift reaction to obtain the additional unknown. So we'll see what additional unknown the question is talking about. And once we obtain the results, we need to compare the mole fraction that we get from our calculation with the values that you can obtain using this equilibrium calculator below, right on this link. So let's get started with this. So for now, let's actually write down um, the chemical reaction equation for stoichiometric methane air mixture, right? So if you let's say if you're dealing with phi of 1, right, then the methane air mixture would look something like this, right? So it'll be CH4 plus 2 times O2 plus 3.76 N2 give you CO2 plus 2H2O plus 7.5 to 1 nitrogen. Okay. Now, if it was for a complete combustion and equivalence ratio of 1, we would not bother doing any calculation, right? We know what the equation looks like. But here we're dealing with an equivalence ratio of 1.5, and we know in reality there's going to be some dissociation, right? So we are expecting many more products than just CO2 and H2O, right? We are expecting CO, we are expecting H2, and we want to understand what would be their mole fraction. So when you want to increase the equivalence ratio of 1.5, basically you simply multiply the fuel side by the equivalence ratio in this case, right? So here the air remains the same, we are just increasing the fuel. So the equation would look something like this, right? It'll be 1.5 moles of fuel plus the same amount of air, giving rise to some moles of CO2, we don't know how many, plus some moles of CO, plus some moles of water in the vapor phase, plus some moles of hydrogen, and 7.52 nitrogen. Nitrogen does not take part in the reaction, so we know exactly how much that is. Now, the first rule of thumb or the first way to solve go ahead with this problem is to simply apply atom balance, right? So let's apply atom balance and try to find out uh, everything in terms of one unknown, right? So here, if you look at it, we have multiple unknowns. We have A, we have B, we have D, and E. There are four unknowns, but you just have three unique atoms in this equation: carbon, hydrogen, and oxygen. So you can only get three equations, right? Three equations, four unknowns, and therefore we need the additional equation, which is the water gas shift reaction, which will help us fix the additional unknown and then solve this problem. So let's start at applying atom balance one atom at a time. So let's start with carbon. So with carbon, we just have 1.5 on the reactant side, and this will be equal to A plus B on the product side. So here we can write B is equal to 1.5 minus A. Okay. Now we can do the same thing for oxygen. Okay. So we have four atoms of oxygen on the reactant side, and this will be equal to 2A. There's oxygen in CO2, there's oxygen in CO, and there's oxygen in H2O. So it'll be 2A plus B plus D. Okay. Now you can simply write D to be 4 minus 2A minus B. Or we can substitute the value of B, which we know is equal to 1.5A, and get D to be 2.5 minus A. We want to write everything in terms of A, right? So bring everything in terms of one and more. And now we can do the same thing, atom balance for hydrogen. We have 6 hydrogen atoms on the reactant side, and this will be equal to the only two places you find hydrogen atoms on the product side is in the water vapor, H2O, so it's 2D, plus in the hydrogen molecule itself, 2E. So this basically means that D plus E is 3, or E is 3 minus D. Again, we don't want to leave it in terms of D, we want to write it in terms of A. So I can write D is equal to 2.5 minus A, which gives me E as 0.5 plus A. Okay. Now here, as we can see, we have written down everything in terms of A, but that's where we stop, right? So we have 4 unknowns, but only 3 equations. So we need additional equation, and that additional equation basically is the water gas shift reaction. All right. So now let's move on. So we have the equation now. Now let's go ahead and make use of the water gas shift reaction. Okay. So when we talk about the water gas shift reaction, we're talking about a particular reaction that's going to help us, a particular reaction that connects the different molecules we see on the product side. Okay. So when you look at the water gas shift reaction, it is basically the reaction of water, H2O, with gas, which is carbon monoxide here, carbon monoxide gas, and these two react to form CO2 plus H2. Now, water gas shift reaction is it's a very useful reaction. It's found in many different systems. It's of course a part of combustion, but it's also something that's used during the production of hydrogen from methane, right? Steam methane reforming plus water gas shift reaction gives you the total amount of hydrogen that you get from any facility which is trying to produce gray hydrogen. So this reaction is useful, and you'll tend to see this very often if you stay around in the chemistry side, or anything to do with chemical reactions, anything to do with energy systems. This reaction is part of it. Now, what we want to do is to find out equilibrium constant, and we want to, of course, find it out at the temperature of interest, which is 1500 Kelvin. Okay, we know that equilibrium constant Kp is given by exponential minus delta G star by RT. So all what we need to find out is now delta G star, right? Now, delta G star itself, we can write it as the Gibbs function for the product, so CO2 plus Gibbs function for H2 minus the one for the reactant. So function for CO minus Gibbs function for H2O. Now we get all of these values from the tables for the Gibbs function that I've uploaded on the Blackboard, and we need to get them at 1500 Kelvin. Okay, so when you obtain those values, you should get something like minus 770,057 for CO2, minus 231,835 for S2, then minus 444,192 for CO, and minus 569,485 for S2. Okay, when you do the math, it comes out to be 11,785 kilojoule per kilomole. Okay, so this is the unit for the Gibbs function that's provided on the table, And this is what you will find. Now that, of course, is part of the problem, part of the solution. What we need is Kp. So Kp is exponential minus 11,785 divided by R. R is the universal gas constant here, times temperature, so 1500. And this comes out to be, in this particular case, it comes out to be 0.38868. Okay, so that's the equilibrium constant, but the question is, how does it help us constrain our equation? Well, if you look at the formulation for equilibrium constant, as we have seen before, equilibrium constant can be written in terms of partial pressures or can be written in terms of mole fractions, right? So it can be written as the mole fraction for the product times the total pressure divided by reference pressure raised to a stoichiometric coefficient, which is 1 on the product side, right, for CO2. So now when we're writing these numbers, right, so this is basically coming from this water gas shift reaction. Okay, so here um, the formula for the equilibrium constant, that is. So this is what I've written here is simply partial pressure for CO2 divided by reference pressure. Same thing I can do for the other product. So the mole fraction of hydrogen times the total pressure divided by reference pressure, and whole thing divided by the same thing. So mole fraction for CO times P total by P ref multiplied by the mole fraction for H2O P total P ref. Now, as you can see, the P total and P ref gets cancelled out. Okay, it's there in numerator, denominator. So what you're left with is mole fractions. But when you even look at the mole fractions, I can write the mole fractions as the number of moles of CO2 divided by the total number of moles. Okay, and the same thing I can do for the others. So number of moles of hydrogen by total divided by number of moles of CO by N total and number of moles of water vapor by N total. Now, as you can see again, the total number of moles also gets cancelled because it's there both in the numerator and denominator. Okay, so what we are coming up with is that this equilibrium constant that we have calculated at 1500 Kelvin, it ensures as this ratio of the product, product of the number of moles uh, of CO2 and H2 divided by the product of NCO times H2O. This ratio has to be has to be followed or has to be respected, right? So this is the thing that helps constrain the different mole fractions for CO2, COH2, and H2 within the initial reaction that we spoke about. Now, where are we going to get these moles of NCO2 and H2 from? Well, this is basically coming from the chemical reaction we just wrote. Okay, so here, if you go back to the previous slide, we came up with some expressions for um, uh, the product side, right? So this is said A moles of CO2, B moles of CO, D moles of H2O, and E moles of H2. The values of A, B, C, and D need to respect the value of Kp at 1500 Kelvin, and it has to be basically, this is the another formula, this is another equation that helps us constrain those relations, right? And so what we are going to do is simply go back and substitute the number of moles for each of these molecules, which we get from this side, A, B, D, and E. These are the moles that we need to substitute correspondingly here, and then we start looking at our solution. Okay, so let's move ahead and do that. Okay, so now going back, basically we have the value for Kp, right? And Kp is equal to 0.38868, and this we said is equal to number of moles of CO2, which is A, as per the reaction, number of moles of H2, which is E, divided by number of moles of CO, which is B, times number of moles of H2O, which is D. Now what we need to do is we need to write everything in terms of A, right? So we just have one unknown and we have one equation. So here I can write it as A times E as 0.5 plus A, okay, divided by B as 1.5 minus A times D 2.5 minus A. Now, when you solve for it, you end up with a quadratic equation, of course, in terms of A. And I'm just going to skip through and write down the final quadratic equation. You end up with something like 0.61 A square, right, plus 2.0547 A minus 1.457 is equal to 0. Now, of course, you can solve for the roots of A. We will take the positive root because A is the number of moles of CO2 and it cannot be negative, right? So it's going to be minus 2.0547 plus square root 2.0547 square plus 4 into 0.61 times 1.457, whole thing divided by 2 times 0.61, right? And here, when you solve for it, the value for A comes to be 0.601, B is 0.898, C, sorry, we don't have C, just to avoid confusion with carbon. D is 1.898, and E is 1.101. Now, these are not mole fractions, these are the moles, right? Moles for the different species. A is for CO2. So these are the moles for different species. So A is for CO2, B is for CO, D is for H2O, and E is for H2, right? So we still need the mole fraction. So the way you calculate the mole fractions is very simple. For example, YCO2 is the number of moles of CO2 itself, so 0.601, divided by total number of moles, which is number of moles of CO2 plus number of moles of CO plus number of moles of H2O right here, which is 1.898, plus number of moles of H2, which is 1.101, plus number of moles for nitrogen. We should not forget nitrogen, right? Nitrogen is also part of the of the product side of the ultimate product side that we have, right? It does not take part in the reaction, but it's still there. So you got to include that. So when you do all that, when you calculate mole fraction the way it needs to be calculated, number of moles for a species divided by total number of moles, right? We should be getting the number that I have written here. We'll get it 0.05. Okay, so this is essentially how you get the mole fractions for all species in here. And yep, once you have the mole fractions for all species, that's what you're looking at. And remember, we solved this problem by assuming that these are the only products, right? There may be more products than this, and we're neglecting them. So this is the only sort of the assumption we are making. Apart from that, we're not really making any other assumption. Okay. Now, when you look at it, if you go to the website and solve for it, you get these results for equilibrium state. Okay, and as you can see, these compare very well. We did not assume any methane on the product side, nor did we assume any oxygen on the product side. And our assumption was kind of okay because you can see their mole fractions are actually very, very small. Okay, so they're almost negligible. We took them as zero effectively, so they turn out to be very negligible. Now, when you look at the mole fraction for nitrogen, as per the equilibrium calculator, our values compare very well, right? It's both of our value and the value in the equilibrium calculator is 0.6256. Same as the case for CO2, CO, H2O, and hydrogen. So whenever we are making a reasonable assumption about the products where you neglect some, of course, some species, of course, to make your calculation easier, but as long as you do it properly, your calculation or your numbers should match very well with what you can get from a typical equilibrium calculator. Now, the way to do that in an equilibrium calculator, well, you just have to plug in the number of moles or mole fractions for the input, mention the different elements there, and importantly, uh, you should remember that we are applying, we are solving this for a particular constraining conditions, right? So if you recall, the way we came up with this equilibrium constant formula for Kp is by making some assumptions. The assumption was that temperature and pressure was remaining constant. And for constant temperature and pressure, the equilibrium constant we said is the equilibrium composition is achieved at minimum value for Gibbs function. And basically we set dg to be 0, right? So it's important that when you are looking at the equilibrium calculator, you take the constant temperature and pressure condition. Otherwise, you're gonna get a crazy answer, and it makes no sense, right? So you should know what were the properties that we constrained for coming up with the solution. If you change the constraints, if you make it constant temperature, constant enthalpy, or sorry, if you make it constant temperature and constant volume or something like that, then of course things are going to be very different, right? So this is solved for a constant temperature and constant pressure scenario. So initial and final temperature will exactly be the same. Initial and final pressure will exactly be the same. Okay, so this is what you're assuming, and for under this condition, this will be the equilibrium composition that we calculated manually, and the same thing that you get from an equilibrium calculation. Okay, so that's it. That's the end of chapter 2.